Welcome to this workshop on on-demand tuning. In this workshop, we'll be looking at a commercial tool for tuning PID control that demonstrates many features you'll find in commercial products for assisting you in tuning a control loop. In this workshop, we'll be using a heater process and tuning a temperature control loop. Initial part of the workshop will be initiating testing of the process to determine the process dynamics and gain. Then we'll look at the way the selection of tuning rule impacts the tuning. We'll also look at a simulation environment in which we can look at the expected control response for the recommended tuning and look at how there's a trade-off between robustness and performance, and then based upon that select the tuning that would best satisfy our needs, apply that in the control loop, and then look at the actual response of the simulated process. The heater that we'll be using in this workshop is shown here. The steam to a heater is adjusted by our temperature control loop to maintain the outlet temperature at set point. So we have a full dynamic simulation of this that we'll be using as the basis for this. As we saw in the control system performance monitoring workshop, there's a tuning environment within that we can now use to go to a particular area or to a particular control loop within an area and select that for tuning. So in this particular case, we're going to select our temperature control loop and then drill into that and look at then the interface for tuning. So for on-demand tuning, this is the interface that would be provided to the user. We'll talk in a further workshop about adaptive tuning, but for on-demand tuning, we see that there's a trend of the PV, set point, and output automatically provided for you for the control loop. The operating conditions, the mode of the control is shown. In this particular case, the control loop is already in automatic, so for us to look at the performance of the process, we're going to put the control loop in the manual and then change the valve by a step and then look at the impact this has on the outlet temperature. So here we changed it by 10%, and in response we see that the valve did change, and now then the temperature is responding to that increase in steam to the heater. This is always a good idea if you're tuning a control loop to first look and see if the process is responding to outputs to the control valve. So if you have a sticky valve or something, this would be the time where you would find that out and know that there's further problems other than tuning. But in this particular case, it looks like the process responded well. To tune the control loop, all a person needs to do is select the step size that will be introduced into the process automatically to tune the control loop, and then hit the test button. When we select test, then the output is automatically put into what's known as a relay oscillation. So initially the output is changed by a step, and as the process starts to respond, it's then changed in exactly the opposite direction. The change is based upon the step size that was selected. As you see, it goes into what looks like an oscillation. It's really being driven though by this relay oscillation technique. And as a result of this variation, we then, in analyzing that, can determine the process dynamics. The ultimate gain, ultimate period, the gain, dead time, and time constant. The process dynamics determine the tuning as well as the tuning method. So in this particular case, if you choose PID, derivatives used. If you use PI, only gain and reset is used. In this particular case, the tuning is quite a bit different than what we currently have in our control loop. So to see how this new tuning would work if we actually applied it in a control loop, we can go to the simulate environment for on-demand tuning. And when we do that, then we're presented with a plot that shows the step response for a step change in set point. Also in the bottom part we see a robustness plot. So the step change, and then we see the valve position that would occur, and then the way the control parameter would come up to set point. So with the recommended tuning, we're at a certain point in terms of robustness, that is, how sensitive are we to changes in our process, and that's indicated here by gain margin and phase margin. By clicking in this area of the robustness curve, though, you notice it has a dramatic impact upon the process response. So by trading off robustness, that is, having less latitude in terms of process gain change before we go unstable, we can get a faster response. Also, by trading off phase margin, we notice it has an impact upon the manner in which we approach set point. We can look at the response for process disturbances as well here for the selected tuning on the robustness plot. If we like what we have, then all we have to do, if we like the response that robustness gave us, is just hit the update. And when we do that, then this tuning will be then transferred to our controller directly within the control system. So we don't have to type that in or anything, just click the update button. It's now transferred to the controller automatically. We can now then go back to our tuning view and then put our control loop onto automatic and see just what we will get in terms of process response. So in this particular case, we're going to go to automatic, and we'll change our set point by a step and look at the behavior. And as we can see here, for the set point change, we get almost an immediate change in our valve. And in response to that, we see that the control parameter comes up to set point very nicely without overshoot, very much like what our simulation environment showed us. So the prediction of what the behavior would be is quite accurate, as long as the process model that was identified is accurate. So as you can see, it's a fairly simple process, basically selecting step size, hitting test, using a certain tuning rule or selecting a tuning rule. Based upon that, then hitting update to get the desired tuning into our control loop.